Um, so thank you so much for coming. I first of all want to thank Pi Ohio. So this is my first technical talk ever. So yay, thank you for coming and thank you for being guinea pigs and thank you for being awesome. So one thing you may notice is my title is a little long. I love when you looked in it and it's like 2 o'clock and it's like ... The whole name didn't fit. But I think it's really important to kind of frame who I am as a coder. So in the title of this talk, you're going to right away see who I am and how I approach machine learning. But again, the name of the talk is that spam in my ham, a novice's inquiry into classification. So, hey, I'm Lorena Mesa, and I'm a complete newbie to machine learning. So let me tell you a little bit about myself. About 3 years ago, I was a policy analyst working in Chicago, worked with a lot of data. I worked at Obama for America, and just started seeing the coolest stuff happening around me. Civic tech was blowing up, a lot of data was being recorded, or rather, data's always been recorded. Now we just have a lot more of it. And one of the first things I started hearing a lot about was big data, machine learning, supervised learning, and I was really curious about what all this stuff was. So now, 3 years later, I do work professionally as a coder, and now that I've got a little bit of coding might under my belt, I said, I want to try my hand at looking at a machine learning problem. So this is a little bit of where this talk comes from, and if you do have any questions, I'm very, very present on Twitter, so I know it's a long hashtag, but spam in my ham. If you have any questions, please feel free to ping me there, or any feedback, please let me know. So, okay, gotta start with this. How many of us have seen something like this in our inbox, maybe not all the time, but at one point in our life? So on the right, it's a photo of an email, and it's really great. It's got an image at the top with some amazing sales pitch. It's like, is your PC slow? Is it full of junk? De-junk and speed up your slow PC. Try computer checkup free. All caps, exclamation, asterisk, more text in the bottom. It's like free, free, free. And yes, yeah, there's a lot of free at the bottom. I didn't take a full image of it, but there's more like free in a big image. It's beautiful. So the other thing I really like is the person who sent me this email. Like, I have a relic of an old AOL email, so this is where I found it. And the alleged sender of this is AOL_memberinfo@emails with a Z .aol.com. So, we all know that this is spam when you see it. There's, this is free, this is the best thing you could possibly use, and of course my email address is so legitimate. Of course I trust this email. So yeah, so that's gonna be spam. So let's kind of take a step back. How am I gonna be approaching today's talk? Well, again, big thing here, I'm new to this world of machine learning, and really I wanted to give a talk to someone who, like myself, could understand. So I'm going to be framing this talk with 3 questions. 1, what's machine learning? That's kind of important. 2, how is classification a part of this world? And 3, how can I use Python to solve a classification problem like spam detection? So the first question, what is spam learning? So this is Johnny 5, great 1980s movie. And I think for me, when I thought of machine learning at first, I envisioned like these, brilliant mad scientists, both men and women, yes, men and women, in white lab coats, talking to Hal and being like, Hal, we are giving you all the secrets of the universe because you are better than IBM, because you are Hal, and you will learn everything and make our future better. Maybe not that ridiculous, but my context of machine learning was very far out there. So what do I do as a beginner? Well, I start looking for some words to describe what the heck machine learning is. So yay, thank you, Wikipedia. Yes, this is actually from Wikipedia. And I mean, that's really one of the first things I did. I'm like, well, what does it even mean when you say machine learning? So rather than read this whole thing to you, I'll just tell you that the part that stuck out to me and made me be like, maybe I can actually understand this, is this last part here. The construction and study of algorithms that can learn from and make predictions on data. So hey, I know what an algorithm is, I know what data is, and ideally speaking, I should know what a prediction is. So let's put these 3 together and explore some more. So let's go to a more awesome source, Tom Mitchell, Carnegie Mellon professor of AI and learning, and just wrote one of the quintessential texts about machine learning, aptly named Machine Learning. So Tom Mitchell can give us a better kind of jargon or language to help us understand machine learning. He describes machine learning as a well-posed learning problem. Or more specifically, and this will be important, I'm going to keep coming back to this, is this definition here. So this comes from chapter 1. We can say a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T as measured by P improves with experience E. So we have a task, we have experience, and we're going to have some way we're going to measure that performance. So experience. You know, when I think of experience, I remember being like 5 years old, very, very sugar hungry, being like, the ice cream man is outside. I have to sprint super fast to go get that ice cream because I must eat it all now. That is not going to happen if I don't get there fast enough. But oh no, what happens if I run really fast and I trip and I fall and I skin my knee? That's obviously painful. So I have that memory of running really fast, falling, hurting my knee, and then learning from that memory and being like, uh-oh, I shouldn't run that fast, or at least I should have a better strategy for knowing when the ice cream man's coming. So for me, when I first thought of experience, I think of human memory. Well, we can actually conceptualize experience in different domains. So let's think about the stock market. If I want to know the experience of the stock market, you know, I can look at historical market data and say 5 years ago, what does this data tell me about the experience of the stock market? How about from last Wednesday, or how about from 8 o'clock a.m. on Friday morning? There's other ways we can perceive experience. So we've kind of talked a little bit about what the algorithm's going to take in, what kind of algorithms machine learning is trying to implement. We talked a little bit about how experience is part of that. So how does classification fit into all of this? Well, classification is a type of machine learning problem. No surprise there. So when we think about classification, let's reframe it with Tom Mitchell's description. Our task is going to be to classify a piece of data. Our experience is going to come from a set of pre-classified training data. And the performance measurement is ultimately going to be the question, is this classification correct, yes or no? So simple question, yes or no. So if we think of spam detection, let's reframe this again in the language of the task, experience, and performance measurement. Our task here is going to be to classify an email as spam or ham. The experience is going to be arrived by using a collection of pre-classified known examples of spam or ham. Again, ham being that it's not spam. And then our performance metric is ultimately going to be, we need to validate if that email is spam or ham. So we'll talk about that a little bit more. So classifiers are great. They can put a metric, and they can tell us about, you know, we can apply a label, we can ask if this label's correct or not, but how are we actually going to do that? Well, here you go, naive Bayes. Wouldn't it be great if I just stopped there and I was like, that's it, we're done. So the type of classifier we're going to be looking at is naive Bayes, and this is actually a snapshot of the math we'll be using. This is based on Bayes' theorem, which comes from stats theory. So naive Bayes, like what is Bayes' theorem? Well, something that's a big part of Bayes' theorem is the way that it looks at events. The idea the idea behind naive Bayes is that if I have one event, the likelihood of that event happening, or the idea that it even happens itself, is going to be completely independent of the likelihood of another event happening. So this assumption is what we call what makes the Bayes' theorem naive. So that's great. I just said something about independent. What does that mean? So let's think of two examples. So, you know, back to stats class. So if we think of flipping a quarter, and I say, what's the likelihood that I will flip ahead 2 times in a row, or what's the likelihood I'll flip tails 8 times in a row? The likelihood of doing of the result of each flip is going to be independent of one another. So 0.5 for the first flip, 0.5 for the second flip, et cetera, et cetera. The likelihood of flipping heads one time and then flipping it the second time is independent of one another. So what is that in opposition to? Well, let's think about an example of a dependent event. A horse race, because I know many of us go to horse races. I've actually been to the Derby. But that aside, when we think of the question, what's the likelihood that horse, you know, I don't know what you name your horse. What's the likelihood of that horse winning the race? Well, we can't really think of that in a vacuum. one of the things we need to consider is like, well, hey, is it rainy today? Is it muddy? Like, is the horse sick? Like, there's a lot of things that can factor into the likelihood of that horse winning. So we say this is an example of a dependent event. There's many things that are going to be impacting the likelihood of this outcome. So let's reframe that in our spam problem. Cleveland Cavaliers. I hope maybe anyone is a fan in here. Oh no. Silence. Yes, we got one. Granted, I'm a Bulls fan, so we're in opposition. But let's think of it like this. If I were to say that the presence of the word Cleveland is independent of the presence of the word Cavaliers, that's going to be in line with the naive Bayes model. When we're looking at spam, we're going to be looking at the words in the email itself, and we're going to say the likelihood of one word is independent of the likelihood of another word. Granted, we know that's not true. Cleveland Cavaliers is a really awesome NBA team, so that's kind of, again, a very naive assumption. Or if we were trying to think of like maybe spammy phrases, like buy now, buy now or forever hold your peace. I don't know what words are actually used, but again, we're going to say the likelihood of the presence word buy is going to be independent of the likelihood of the presence of the word now. It's cool. Let's go back to that math. So what our spam filter is going to do is we're going to actually try to calculate the probability for each category, which is spam and ham. We only have two categories, two discrete categories that we know about. So if we are to revisit the Bayes theorem here, we've got three parts. So this first part here, what's called the likelihood of the predictor in the class. Our predictors are going to be the words in the email itself. So I'm talking about the body. So if I have the word free, I want to know how many times I've seen the word free in all of my data that I have for ham, and then all of my data I have that's spam. So I'll do that for each word. So let's say I have 15 words in my email. I need to calculate the likelihood of each word by itself and multiply that all together. We also then multiply it by the prior probability of the class. So if I have 150 emails that have labeled data, and then I go to classify a new thing, I can say, okay, well, how many of the previous examples were actually spam? That's going to be my prior class probability. So we multiply all the likelihood indicators of each word. We multiply that by the prior probability of the class. And then that last bit there, what we want to do is divide by the prior probability of the predictors. So our words are our predictors here. So if you think about the word free, so out of 150 emails, how many of those emails had the word free? Well, 72 out of 150. In this case, though, we actually don't care about the prior probability of the predictors, because when we run that math for calculating the likelihood of ham, or running the math for calculating the likelihood of spam, that value is going to be constant. So we don't need it. We're not even going to worry about it. So we're only going to worry about the likelihood of the predictors themselves and the prior probability of the class itself. So yeah, so naive Bayes then ultimately, and here's map, fun word. So ultimately what naive Bayes will do, it's going to run that calculation for the number of categories you have, in this case ham and spam, and ultimately it's going to pick the label that has the maximum a posteriori probability. And when I say a posteriori, that means we're looking at data that's already happened. We know what that data represents. So using the frequencies from data that we already know, we're able to calculate the probability of each category, and we just pick the one that has the higher probability. So awesome. And again, P of X is identical, so we don't really care about that. So why naive Bayes? There's definitely other algorithms you can use, like nearest neighbor. For me, because again, like I said, I'm a beginner, this world is new to me, naive Bayes, the math was very accessible, and I found it fine for what I needed to do for learning a small problem. So that's why I chose to move forward with this one. But there's definitely more sophisticated classifiers you can use, and I encourage you, if you want to do that, go forth and conquer. All right, cool. So how do I actually use Python to detect spam? Okay, so I was a little lazy. I did not want to label all my own data. So not like I cheated, but I went to a source that actually had labeled data for myself. So Kaggle's a really cool source for anyone interested in data science. Kaggle in the Classroom has more beginner-friendly kind of problems. And for me, I was like, this is perfect. It's all labeled. I want to use this. So with the labeled data that was provided, there was 2,500 emails that's considered the training data, of which 1,721 of them are ham, and they have a label of 1. And spam is 779, and they have a label of 0. So the CSV file would have the ID and then the prediction of either 0 or 1, and then the emails are actually with some HTML in it. So what I actually ended up using was Python 2.7.9, and I just used three little tools. I used the email package to parse emails into message objects. I used LXML to transform email messages into plain text, and I used natural language tool processing kit to filter out stop words. I'll talk about that in a second. Okay, cool. So we've got our data, it's labeled, we know what tools we want to use. So let's train the spam filter. So again, training means with all the classifications that I already have, I need to go through each email and find out how many times I see a word in each category, and then also I need to find out how many instances of spam and ham I have. So what you'll notice here is start by tokenizing the text. I'll show you a slide of what that means in a second, but basically I'm breaking up each email into a bag of words, and then using that bag of words, I say, cool, tell me how many unique words are in each email, tell me the frequency of those words in each category, and then let's go ahead and increment how many times I see each category. So the stemming words here, I took a very kind of simplistic example with my Python toy example. So if you wanted to treat the word shop and shopping alike, you definitely can do that, and that's called stemming. I did not implement that for this, so if you're curious about that, feel free to go forward and do that. I did not do that for this. And Laplace smoothing is something I'll talk about in a moment. So our bag of words, literally a bag of words, very exciting. The one thing I did make use of here is, using a regular expression, broke it up. So after I parsed out, I used LXML to turn it into plain string. I then say, okay, so long as my word is not in the list of stop words that the natural language tool processing kit has, let's go ahead and keep it. So stop words are words like the, words that are abundantly used in English. So when I say tokenize text into a bag of words, this is kind of the way I implemented it. Uh-oh, problem. What if I have a new email that has a word I've never seen before? So apparently I'm obsessed with the word free. So if I have a new example, so I've trained my algorithm, I've made all the frequencies, I've counted how many instances of spam and ham I have, and now I go to classify a new email. If I have a word that I've never seen before, I'm not gonna be able to say, well, what's the likelihood of it? It's just gonna be 0 out of how many words I have, and that's gonna throw our multiplication of all the likelihoods out the window. So there is a few ways you can handle zero word frequencies. I opted to use Laplace smoothing. It seemed to be the most accessible for me, and the idea here is you can add a small positive, a small epsilon. In this case, I just used a constant 1 to all counts to prevent this. So I know that's a lot of code, and I actually do have my code on GitHub if you want to rip it apart and tell me I should work more on make it more sophisticated. So actually when you actually go and classify, I break up the email into a bag of words. I then go get the frequencies for each word to get the likelihoods of all the words, multiply it together by the prior probability of each class, and you'll see this get predictors probability. There's a big note here. So I'm only working with 2,500 pieces of training data, and there was 1,827, I believe, examples of things I had to classify. So what happens if you're working with like 100,000 records, 1,000,000 records? Because obviously working with just 2,500 pieces of data is not very big. Well, this is something I don't normally encounter in my day-to-day. I don't do scientific computing. I'm not working with lots of data per se. So I never really ran into the problem with floating point underflow, when you need very precise math. So I actually had to look that up. I'm like, what do I use? What do I have available in Python that allows me to do floating point arithmetic? So I ended up using the decimal object, which allowed me to do what I needed. But another workaround, rather than multiplying all the likelihoods together by the prior class probability, you can use the log of those probabilities and the prior class probability and add everything together. So that is one thing to keep in mind. And again here, for words that I haven't seen before, treat it as value 1, and then I'll have to adjust my accounts for all the words and all the class prior probabilities accordingly. Sweet. So we've trained, we've kind of looked at what classifying an email would look like. So let's go ahead and just run it. So when I went ahead and just ran against all the examples that were unlabeled, I came to have around 31% spam, 68% ham, and that's, again, just using the words as the predictors themselves. So that's great. I've done a task, I've used some experience, but what about a performance metric? How am I going to do that? So the data that I was supposed to label did not tell me, I did not have an answer key that said this is actually what this is supposed to be. But I did have all my training data where I could instead maybe train on some percentile or some percent of the training data and then try running it on the balance. So that's what I did, just for a small idea of what a performance metric would look like. So I broke up my training data into 90% to train on, and then performance measurement on 10%. In about the worst case, it kind of was, there was a median of about like plus or 3, where I would have a deviation of up to 30 wrong, up to 33 wrong, around 24, about 24 incorrect. In this case, I was around 89% performance measurement, which from what I can tell in the Kaggle discussion, it was like really hard not to get 90%. So it's kind of interesting. It's like, you are going to probably get that with just this really simple implementation. So how do you get that extra 10%? How do you go all the way and just know everything about spam? So I'll address optimization in a minute, but something else I did want to point out too is that there is potential for false positives. So in my world, I do like Patagonia, and I do sign up for their emails. So I don't know if you've ever seen this, but there is a potential for false positives. In this case, Patagonia, they sent me a marketing email, like, we have stuff on sale. And I was like, I do want this. But you'll notice that Google's spam filter, it says, well, the reason this is marked as spam is because it contains things that are typically used in spam messages. So the idea of typically used in spam, again, there's some assumptions being made. You know, the likelihood of each word happening by itself, that's a small, very naive kind of image of the world. And again, I'm only looking at one type of predictor. So granted, Google has a much more complex algorithm, but you know, there is the idea you have to think about. You need to have a really robust way to measure the performance. So while I did take one step in that direction, there's obviously a lot left for me to implement. And you know, as a good Samaritan, you can always tell Google, yes, this is spam, or no, it isn't, and give them more data to make their stuff so much cooler. So drawbacks of naive Bayes. Again, independence assumption. This is a simplistic kind of model of the world. And also, that simplistic model of the world is going to allow us to overestimate the probability of the label that's ultimately selected. So naive Bayes is good if you just want to make a decision and be like, okay, it's this category, it's not. If you care about precision, this might not be the best model for you. So again, inconsistent labeling of data could also be another problem. So this is a supervised learning algorithm. We're telling it, this is the stuff you should learn from. So what happens if I had like 20 undergrads who are labeling all my data, 3 of them saw the same email, 2 of them said it's ham, 1 of them said it's spam? That inconsistency could lead to problems. So to improve our performance, we could think of other things, like what's the subject of the email? How many images are in the email? Who's the sender? Is there a lot of weird punctuation? Or, you know, simply put, we can just have more data. Yay! So which is really important, right? With more data, you're able to have a more sophisticated understanding. So if you're curious and you would like to learn more, I highly recommend using Kaggle. And again, their classroom one is more beginner friendly, but they have amazing competitions where it's like, we have a field of satellite. We have a satellite field, and we want you to track asteroids. Here's some data, and it needs to be like this. So if you're amazing and you want to do that, more power to you. But the classroom is a really good place to start learning as well and have pre-labeled data should you want to not do all of that. Of course, O'Reilly's books are great. Introduction to Machine Learning with Python, that is my current read right now, and I love it. And then, of course, your lovely, friendly local Python user group, because we love them. So that's pretty much the end of my talk, but I would be very open to anyone. Yeah, this is how I kind of felt at the end. I was like, I learned a lot, but am I overestimating the likelihood of that thing being that thing? So, I would love some feedback, or if you have other tips for next kind of steps, I would be very curious. Again, this code is living, breathing code, so please feel free to go check it out, tweet me, let me know if you have other ideas, maybe something I overlooked. And I am trying to work on the predicting altruism through free pizza right now. It's another Kaggle competition. I think it's really great. So thank you so much for your time today. Oh, sweet. I never know. Okay, yeah, I guess I got 3 minutes. I went a little over.
Can you tell us more about altruism through free pizza?
I thought, okay. Yeah, so basically it's from Reddit it's from subreddits, and the idea is like you did something that was cool for this community, so they sent you free pizza. So the idea is to try to find some metric of like what altruism is, and then once you have that metric, see if you can actually predict when pizza is going to be free for someone. And they have some data already, but it's meant to be like an ongoing competition for a year. I just thought that one was great. Anyone else? Uh-oh.
What were some of the other algorithms people tried on Kaggle?
Oh, yeah. So I know Nearest Neighbor was one of them. I do know, so I haven't played with SVM's support. I can't speak right now. I know some people used SVMs. I have not played with those, so I can't really speak to it. But I also know that there was like a grad student, I think at Carnegie Mellon, so where Tom Mitchell is, who was like doing some amazing stuff and had, I believe, 1 million pieces of data he was trying to classify. So I was like, yeah, you're getting a gold star for the day. Yeah. Any other questions? Cool. Well, thank you so much again for coming. I appreciate it.